All right, welcome back. Now we're going to start talking about units and why they are so darn useful, right? And in the process, we're going to talk about shear stress, which is a tremendously important concept in fluid mechanics. Um, so we want to know, let's say we have a problem where we're trying to figure out what the drag stress is on two plates that are moving when separated by a fluid. So our top plate here is moving with a velocity v. Here's our top plate. They're separated by a height of h. The fluid has properties of density and viscosity. This is, by the way, the symbol for viscosity, mu. That is almost universally used, though not quite. In fact, this is what's called the dynamic viscosity, and we'll get into the difference later. And we haven't drawn it yet, but we should draw in a coordinate system here of x and y, right? And so we want to know what the drag stress is on two moving plates separated by a fluid. So if we write down all the important parameters here, the velocity of the plates, the density, the viscosity, the height, and the shear stress, let's write out the units that are related, units for each of these things, right? So velocity is length per time, and we're not going to pin ourselves down in either imperial or metric units right now. We're just going to use the generic symbols for these. So length and time, L and T. Density is mass per length cubed. Viscosity is a mass per length time. A height is obviously just a length. And a tau, our shear stress, is and I'm going to pause here because this is an excellent spot where we can talk about active learning again. This is actually something you could finish, right? So one of the nice things about these videos, and one of the things I'm going to encourage you to do, is when I'm about to go do something, pause the video and just try to do it yourself, right? It does not get more active than that, right? It does not get more active than just doing it yourself. And then when I go and do it in the video, you can double check it. So hopefully you're going to pause the video. I don't know why I just paused there, because clearly if you pause it, you're not going to hear me. Pause the video, do it, and then restart it. But find the fundamental units for tau, or shear stress. Okay, so the fundamental units for tau are force over length squared, right? It's usually newtons per meter squared, but we're going to say force per length squared. And the fundamental units on force are a mass times a length per time squared divided by a length squared, which, if you cancel stuff out, ends up giving you mass per length time squared. Great. So we are trying to determine a functional relationship between these different parameters here. And if we want to try to do this, we can actually try rearranging these different parameters solely based on their units and see if that gives us something useful. So we want to figure out what tau is equal to. If we do tau is equal to something, we can say that our mass per length time is equal to, and now we can go and look at these and try to play around with them and figure out how we can get them to work. And it requires a little bit of understanding about the physics of fluids too, which is one of the main reasons why you're taking this class, is to kind of get an internal, intuitive feeling about how the physics works. We know, you can imagine anyway, that if you're taking two plates and sliding them past each other, does density or viscosity matter more? And remember, viscosity is how thick something is, how viscous something is. So honey has a lot higher viscosity than water. So if you put honey between two plates, or water, which is going to have more shear stress when you move them at the same velocity, right? Or density, does density matter more? So if we wanted to compare two fluids that have vastly different densities, you can compare mercury and water. Mercury has a very low viscosity, similar to like water has a very low viscosity as well, but mercury has a much higher density. Is mercury going to cause a lot more shear stress than water? And the answer is, you can kind of intuitively tell us, you know, honey is going to cause a lot of shear stress. It's going to be very hard to push the plate fast enough to maintain the same velocity as you would if you put water in there. So we know that viscosity is going to be very important. So let's try by putting viscosity length times squared. Sorry, I didn't write that down right for the tau. So let's put viscosity here. That's a mass per length time. That's great. Now we have to multiply this by things that will eventually give us the units over here on the left. We already have mass. That's great. We need an extra time. There's only one thing with time on our variables that we have. So let's multiply, and we need time on the bottom. So let's multiply it by our velocity. So we have viscosity times velocity times a length over time. Great. Now, unfortunately, that length cancels out the length down here. So we need to now divide by another length. Where do we have another length? Well, we have a length in h. And so we can actually divide by h times 1 over L. And now we get our units to match up. And this is our estimate of the equation that would help us model the shear stress on this upper plate, which would look something like this, right? If the velocity is going this way, the shear stress is going to try to oppose that velocity. This is our tau here. So we're trying to model what that tau is, predict what that tau is, and this is the equation that units gave us. And actually, that is the right equation for this particular problem. The velocity distribution is going to look something like this, where we have a high velocity at the top, zero velocity at the bottom, and we'll get to it eventually. But tau, if we're doing a two-dimensional problem like this, is equal to mu, our viscosity, our dynamic viscosity, times our du dy, where u is the x component of the velocity and y is the y direction, obviously. So what we care about with this derivative is, how does the x component of the velocity change in the y direction, right? So as we move up, is there a change in the x component of the velocity? And there is. It increases as we move up, right? So this would be a positive quantity here, right? Great. So normally, this quantity of viscosity is in normal fluids, is a constant, right? It's mildly dependent upon temperature for water, barely dependent upon pressure. It's actually mildly dependent upon electric field. Like it varies based on your environment, but we can call it a constant and actually have it work for most problems that we're doing, right? These normal fluids are called Newtonian fluids, right? The opposite obviously would be non-Newtonian fluids. So let's look at what Newtonian fluids look like. Newtonian fluids, if you have two plates like this and you're calculating the shear stress, then as you change the shear rate, now the shear rate is the rate of change of velocity between the two plates. So if we look at these two plates again, the du dy is a shear rate, right? The units on that are going to be, if we look at it, we have a velocity, right? Okay, so a length per time, and we're taking the derivative with respect to a length, so du dy, so we divide it by a length, which equals 1 over time. So those are units, that's a shear rate, has units of 1 over time. And there are two ways we can increase the shear rate within a fluid. We could decrease h, make h smaller, which would make L here on the bottom smaller, which would make the entire thing larger, because you put a smaller thing on the bottom, it makes the whole thing larger. or we can increase the velocity of the plate on the top. Either one will increase the rate at which the velocity changes as we move vertically through the fluid, right? So the bottom is called shear rate. So you can, the way I like to think about it is, let's not worry about making the plates closer together. Let's just increase the velocity of the plate. So V increasing in this direction. And tau is the shear stress on that plate. Well, for a Newtonian fluid, this produces a straight line. If we double our velocity of our top plate, if we double our shear rate, we double our shear stress, right? And it turns out the slope of this, or y over x, is equal to mu the viscosity, right? Which is equal to tau, our shear stress, divided by, which is y, divided by x, which is our du dy, which is our shear rate, right? Now, there are lots of fluids that do other things. So if we go over here on this plot, we can talk about yield stress fluids. So these are fluids that you push on, them, they don't do anything, and then all of a sudden they start flowing like a Newtonian fluid. These are yield stress fluids. A good example of this is ketchup, right? Ketchup will stay in a bottle. We're not talking about squeeze bottles here. I'm talking about the old school glass ones. Will stay in a bottle until you hit it. And if you hit it, then suddenly that liquefies the, produces high enough shear rates, produces high enough shear stress to allow the fluid to flow, and then suddenly it starts flowing like a Newtonian fluid. There are also fluids that are called shear thickening. So these fluids start out thin, right? They have small amounts of shear stress for a given shear rate. And as you increase the shear rate, as you increase the velocity of that top plate, the apparent viscosity increases and the shear stress increases as well. And there are also shear thinning fluids too, which do the opposite. And there are examples of both of these in your life, right? So an example of a shear thinning fluid is latex paint. Latex paint, the reason it works so well is when you brush it onto the wall, you are creating a high amount of shear, right? Let's see if I can draw a wall. This is not gonna be pretty, so bear with me. Here's a wall. Wall's easy. The hard part is, let's try to draw a brush. So if we draw a brush, we're gonna draw the bristles. Here's the bristles, like this. The bristles are squeezing the paint. Here's our paint. And the bristles are moving up, because I don't know why you're painting up, but you're painting up, and they're dragging the paint along with them, right? And because they're moving at a velocity v, and the gap between the bristles and the wall, h, is pretty small. It's very small actually. Remember for a simple two plates that our shear stress is equal to the velocity divided by h. It's not exactly true here, but it's a good approximation. A high velocity with a small h means we have a very high shear rate. High shear rate, which means we're in this region here, which means our paint appears to be thin, right? It has a very shallow slope. X and Y is shallow. It has a small slope, and so it appears thin, so it goes on very easily, right? And goes on very, makes a nice even coat. But then when you take the brush away, it moves at a much slower rate because the only thing pulling it down now is gravity. And because it's moving at a much slower rate, its shear rate's a lot less, and its apparent viscosity, which is y over x, right, is much higher. Right? And that's the whole reason why latex paint, not the whole reason, there's lots of reasons why, but latex paint is so darn useful. Now, shear thickening fluids, you've seen, I'm sure, videos on YouTube of this kind of stuff, you've seen people walk across cornstarch pools, right? If you haven't, stop the video and go look at it. It's amazing. It's incredible. And what's happening when people walk on cornstarch is, I'm going to draw a heel now. This is going to be less than good. Here's their heel. Great. I guess then their calf, who knows? So their heel is going down, right, when they run on the fluid, right? And when their heel hits the fluid and it starts going into the fluid has to move around it like this. So it goes this way in order to move around the heel. Meanwhile, out here, the fluid is stationary, right? And so we have fluid that's moving around the heel like this, and it's slow, and it's decreasing the velocity till it gets out here to no velocity. And as we know from a shear thinning fluid, if you have a high shear rate, so if you're pounding your heels into the liquid very fast, you get a high shear rate here. du dy is high. It's gonna behave like a very thick fluid, right? Let's look at this. Y over x, y is much larger than x. We're gonna have a, remember, because y over x is equal to our viscosity, it's gonna look like a very viscous fluid, which is why when they run on it, it seems to be stationary. When they stop running and they just stand in the cornstarch, suddenly now the shear rate falls. We go down the curve in this direction, and the shear rate appears to be much less, and they slowly sink into the cornstarch. And actually, it's really gross. If you watch them, they'll put their hands into it and move their hands around, and it appears as though stuff is growing onto their hands. And that's just because near their hands, there's a high shear rate, which means it appears much thicker fluid than away from their hands. So it appears as though it's sticking to their hands, but really, it's just solidifying because it's being moved, right? It's really fascinating stuff. And they're successfully working on body armor that uses this to be flexible when you're moving around, when your body's moving around. You can't tell, but I'm pretending to move around. You should too, it's really fun. And then as soon as something hits it that has a lot of kinetic energy and is moving fast, like a bat or a bullet or something like that, the amount of shear greatly increases because the velocity greatly increases, right? A bat hitting you is going to move much faster than you twisting around or moving your arm, right? And that increase in shear rate will cause it to stiffen up and absorb a lot of that energy and hopefully protect you. So, I've already talked about these, so why don't you pause the video and fill these in. I'll give you, pause the video, fill these in. Great. So don't flow until a minimum stretch, catch up. And hopefully you thought of another one, which you use, well, some of us use every day, toothpaste. Gets thicker as shear rates increase, right? So I gave you one, cornstarch. Can you think of another one? Pause the video if you have to. But if maybe you've used this, maybe you haven't, but silly putty, right? Silly putty flows, but then if you pull it really fast, it literally shatters, right? It literally fractures because it gets so stiff. And it gets thinner as shear rates increase. So a shear thinning fluid, I gave you latex paint. Another example is actually shampoo. You can look at videos of people drizzling shampoo onto into pools of shampoo, little like cups of shampoo, and it will actually produce these jets, which are a result of shear thinning, which are really cool. And the mechanical reason for this happening is cornstarch and silly putty both have very long polymer chains. So these polymer chains get very entangled, right? And then if you try to shear them like this, they get knotted almost. Like if you push them really fast, they stick each other hard, they get all tangled up. It's just like if you were taking a bunch of Christmas lights out of a box, try to pull them really fast apart. right? They're going to get stuck. So long chained fluids or solutions like cornstarch will be shear thickening, right? If you make these chains shorter though, they will be tangled. Well, let's keep our color scheme consistent. They will be tangled at first, but then as you shear them, they align with the shearing of the fluid and slide right past each other, which is why shampoo has, what's it called? Surfactants in it, and that are basically long chains where one end is hydrophobic and one end is hydrophilic. But those chains still get entangled in each other. But the end result is that it's a shear thinning fluid because those chains can align as you shear the shampoo, right? It's also useful for getting it into your hair and producing bubbles, right? You shear it to produce bubbles, and then the bubbles stay because there's not much shearing going on, right? Cool. So let's do a quick example and then be done. What is the moment required to turn this top plate at a velocity omega? So what we have here is we have two plates on top of each other. Think of this like literally a record being suspended right above a record player, or I guess literally two plates that are separated by a small distance h, right? And we're going to turn the top plate with a angular velocity omega and keep the bottom plate stationary. And these two plates both have a radius of big R, and our dimensions are going to be our radius and a theta going around our circle and a z going upwards. See. So step one for every problem we do is to choose a model. Choose a way of predicting future behavior of physical systems, right? So in this case, I've given you a model already, and that model that we're going to choose first is that our shear stress is equal to mu du dy, which is equal to, for a flat plate, and this is kind of a flat plate, is equal to mu times v over h. So we're going to try to use that in this problem. Then our second model we're going to use is that our moment is equal to our radius crossed into our force. So if we know our force and we cross it into our radius, we can calculate our moments, right? So step two, make our assumptions explicit. This is so important, and I'm going to hammer on this throughout the rest of the semester. And there's two reasons I'm hammering on it. One is that it makes the graders' lives easy. In every problem that I have them grade, I am going to do exactly what I'm doing here, which is where I list out the assumptions and I'm going to give them a certain number of points. If you list out the assumptions just like I do, you make the graders' job easy. They can just be like +1, +1, +1. They're happy, and if they're happy, you're happy, right? No grader likes to take points off of the work that they're grading. If they do, I fire them, right? They like having it be easy to grade when everything is correct. So, and more importantly, not just being correct, but easy to see. Remember, for our homework, we're going to be grading your work, not your answer. So let's do it here. Make our assumptions explicit. And this is the only time we're going to make this assumption, because for the rest of the semester, we're only going to be dealing with Newtonian fluids. But let's say Newtonian fluid. We weren't told what it is, so we're going to assume it is, right? B, and this is a really important one, our radius is much, much greater than our height. So that means our plates are close to, the distance between our plates is small compared to the radius of the plates. And what that means is that we can ignore a lot of the stuff that happens at the edge of the plates, because what happens on the inside is going to dominate the behavior, right? And C, we are going to assume that W is small. I think that was a mistake. I think I wrote that down last year and it's not actually needed. Cool. So let's work towards a solution here, right? Combining models if we need to. So if we look at our model for a moment, right? If we take 2 and make it 3. And I'm going to be doing this throughout the semester where I label my equations and describe where I combine equations, how I'm combining them. And I highly recommend you do it too, because if you make the graders happy, they're going to grade. It's just easier for them to give you a good grade, right? Oh, I forgot the other thing. The reason why we do this. We make things easy for people to read because rarely will you ever be the only one working on a project forever, right? You might be working on it for a while. You might even finish it if you're lucky. And then somebody has to come back and look at your work to figure out how to troubleshoot it or how to improve it or something like that. And you want to make it as easy as possible. Sometimes that person is you. You're likely not old enough for have this happen yet. I'm nearly 40, and it's getting to the point where I have to look at work, excuse me, look at work that is old enough to drive, right? And I don't remember doing it. And I have to look at my own work and go, oh, shoot, what did I do here? And you quickly learn that the more explicit you are now, the happier you make future you or future people working on your stuff or the graders, right? It's just making, I know it's a cost in the moment, but in the future, it pays off large dividends. All right, so we start with model 2, which is moment is equal to R cross F, and we convert it into, we restate what F is, right? So F is, so we take our moment is equal to R cross F, but F is actually equal to tau times A, right? In that moment. Now, we're going to have to do an integral because our velocity is actually changing as a function of our R, right? As we increase our R, our velocity is equal to R times omega, right? So as our R increases, our velocity increases, which means our shear stress is not constant on our plates. It starts at 0 in the middle and gets a maximum on the outside. So we're going to have to integrate, right? And if we know we're going to have to integrate, that means we should, by the way, I'm doing this problem and it's a difficult problem, and I don't expect you guys to have been able to do it on your own, which is why we're doing it together, right? But what I want this problem to do is to illustrate how we start with models and kind of work our way towards answers. So we're going to rewrite this now and talk about differential moments, which is equal to a radius crossed into a shear stress, which is a point quantity, right? And we got to multiply that by an area, which is we have to make a differential area, which is a 2 pi r dr. So you're asking, well, where did I get that? Well, if we look at our plates from the top, our system is axisymmetric. No matter where we are in theta, this is theta, it's the same. It's the same here, it's the same here, it's the same here, and all these places have the same r, right? So if we draw a circle, all of the area of the plate on that circle behaves the same. And if we want to make that a differential area, we can just make it a little bit thick in this direction, make that a dr. And the area of that strip that goes around is pi r dr. I think this is called ring integration or something like that. You've done it in Calc 2 or 3. I can't remember which one does that. But. So we're going to convert this now a little bit more. We're going to go 4 to 5. Our dm, we now want to get rid of the vector if we can. It turns out that our radius and our force, our shear stress, are always perpendicular to each other. So when we take the cross product, the result of the cross product is just the multiplication of those two things. So we can just write that dm is equal to tau times r times 2 pi r dr. If you want to be technical about it, there's actually a sine of 90 degrees in there, but that's just equal to 1, right? Now, we have a tau, and that's an unknown, right? We know we have an r, which we can integrate over because we have a dr, so we're not worried about that, but we do have this unknown tau here that we need to figure out. We need to get the tau in terms of variables that we either know or can integrate over like R. So we're going to combine 5 plus 1 into 6. So we're going to take equation 5 and equation 1 and combine them into equation 6, which says that dm is equal to mu v over h times 2 pi r squared dr, where we just combine these two r's here and here and do an r squared. Great. Do we know, so let's go back to this equation. Do we know everything? We know our viscosity in theory, right? We've assumed it's a Newtonian fluid, it's a constant. We've been given our H, it was labeled in our system, but we don't know our velocity, right? But I did say up here that our velocity is equal to R times omega. So let's substitute that in. So 6 to 7 dm is equal to mu times omega times r over h times 2 pi r squared dr. And now we can integrate both sides. So this just becomes m is equal to, we have an r cubed actually here, dr, right? So if we, m is equal to the integral from 0 to r of dm, which is equal to the integral from 0 to r of mu 2 omega over h pi r cubed dr, which is equal to mu pi over 2h omega r to the fourth, integrated from 0 to big R, which is equal to mu pi omega r to the fourth over 2h. Cool. So we have a model now for calculating the moment given a viscosity of a fluid, a rotational speed, the radius of the plates, turns out it depends on the radius of the plates to the fourth power, which is interesting, and the separation of the plates, right? And what we've actually modeled here is something called a rheometer. Because you can create plates that you know the radius really well, check. We can know the separation between the two plates. We can set the rotational speed. We can measure the moment. And as a result, the only thing left to calculate is the viscosity. And if we do that, we can use this as a way to measure the viscosity of fluids, right? And the things that are required in order to make this accurate are that R is much, much larger than H, and an assumption that the fluid is Newtonian, right? Although in reality, yeah, it has to be Newtonian for this particular method. So, cool. All right, next lecture, I believe, is going to be about pressure.